We will switch to English if it's okay.
We switch to English.
Life happens in a very weird superposition between Spanish, English, and sometimes Catalan in Barcelona, of course. So, well, welcome everyone to this seminar series. Today we have Federico Holik, who is a close friend from me, but also from all institutions in Argentina. Federico is associated to Instituto de Física La Plata, and also is currently also associated to, correct me if I'm wrong, to Salerno University, Cagliari in Italy. And he is an expert in quantum computing, quantum information, information theory, and beyond. And Federico is the leader of the quantum logics and computing group in La Plata. Is working a lot of on NISQ devices and bringing sophisticated tools from quantum information theory to benchmark current devices. So I thought it would be a super nice contribution to our seminars. So Federico, maybe all the stuff I said by now is wrong, so you can correct. But thank you very much for joining us today.
Thanks, Matthias. Thanks, Matthias, for this great presentation. Just two corrections. The group is called Quantum Logic Proofs Probability, but of course we do quantum computing. And also, yeah, I'm a quantum foundations guy, so you will see that this has some technology discussions, but also some deep foundations of physics, I hope, discussions that I want to encourage you to join and study this kind of stuff. So the talk is called Simulation of Genuine Multipartite Non-Locality as a Tool for Benchmarking and Calibrating Quantum Processors. I will explain first the motivation, just in case you are not so familiar with the technical details of this, so you just understand the idea. So one of the main motivations to justify the development of quantum computers is the belief that they have the ability to efficiently simulate many body quantum systems, with, of course, applications to chemistry, medicine, materials design, and all the good things that you hear about quantum computers. But in this work, we asked a simpler question. To what extent can existing prototypes of quantum processors simulate quantum non-locality? It turns out, I will show you that this is not an easy task, as you will see. And the key observation we do is that determining to what extent a given processor can simulate genuine multipartite non-locality can be useful for assessing whether it is functioning correctly or not. Therefore, it can be an important tool for users to decide whether they will run their algorithms or not, as well as to determine which devices they should buy or hire or use. And it also has benefits for the provider of quantum processors, because naturally, these techniques can be also used for calibration and benchmarking. If you are not familiar with this problem, think about this. Today, we have multiple vendors offering different types of quantum processing unities, both as commercial devices and cloud-based services. However, in the NISQ era, we have noisy prototypes. They have a lot of imperfections, and there are significant performance variations across the different platforms or prototypes. And these disparities persist even when you compare devices with the same architecture. No two superconducting quantum qubits processors perform in the same way. And this is true even for replicas of the same model. If you buy two IBM quantum computers of the same model, very likely they will have a different performance. At the same time, the same physical device will display differences in performance at different moments of time. So you need to calibrate it all the time, every day. some devices are calibrated after each run of a shaft. And of course, different qubit subsets within a single processor might perform differently. So you need to know how things are working. And if you are going to run your algorithms, you need to know which are the qubits that are, or the sets of qubits that are best performant. And then you must choose. So in the NISQ era, users and providers are forced to make choices. Should they buy it or not? Should I fix it or not? And more importantly, users should be able to test quantum processors without revealing what they want to do. So there should be a test layer before buying a higher or hiring a service for the user. This is from the point of view of the end user. And also, it is important to benchmark. There are two tools. Sellers, so this kind of tools, this non-locality benchmark could be also interesting for sellers because they are interested in showing how strong their devices are in terms of quantum resource. So how much non-locality a given quantum processor is able to simulate. We claim that tests based on genuine multipartite non-locality constitute a key tool for all these tasks, possibly, of course, in combination with other tests. We are not claiming that this is the only test you should consider, but we think that it should be included among the technology standards. So in this talk, I will try to convince you of these ideas. And the general features are that this type of test is based on ideas taken from foundations of physics, from fundamentals physics, and it is a test as a whole. It is not restricted to single qubits or pairs of them. It tests a given set of target qubits as a whole. Now, the method relies on establishing correlations between qubits across distinct and incompatible measurement contexts. As such, it functions as a test of quantum contextuality, leveraging non-Clifford resources in the process. Okay, so I've been speaking about quantum non-locality. I will try to give an idea about this. We can go fast or slow, and you should let me know during questions, so you get the main point about this. As you know, there was a big debate in the foundations of physics at the beginning of quantum mechanics between Einstein, Podolsky, Rosen, and Bohr. It is usually called the EPR-Bohr debate. And they defined a reality criterion. And they said, if without in any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. And this is, of course, in tension with what happens in an entangled state. Now, this is the infamous example used by Einstein, Podolsky, and Rosen. It's a system in which if Alice decides to measure position, she will be able to predict the position of Bob's particle, and the same happens with momentum. Nowadays, examples are simple and use spin, like a discrete variable. This is posed in terms of continuous variables, but the idea is that if Alice is able to predict the value of Bob's variable without in any way disturbing it, and this is the assumption of locality, because particles are assumed to be very far away, so there is no way, if you assume locality, in which Alice's measurement will affect Bob's. Therefore, there should be an element of reality associated to Bob's particle. And therefore, they conclude either locality is wrong or quantum mechanics should be incomplete because the wave function is not able to predict Bob's outcome. Therefore, there should be something there going on, something that we don't know, and the wave function is not telling us. So they say, since at the time of measurement, the two systems no longer interact, no real change can take place in the second system, in consequence of anything that may be done to the first system. So they conclude, this suggests that the wave function does not specify all elements of reality. Then Einstein, Podolsky, and Rosen are forced to conclude that the quantum mechanical description of physical reality given by wave function is not complete. So this inspired Bell's works during the 60s. Now he considered a spin scenario where you have this element here, which is the probability of Alice measuring bold A, bold B, and obtaining the results A and B. He says, okay, let us assume that Einstein EPR are right, that their argument is right. And so he says, let this more complete specification be affected by means of parameters lambda. So he says, let us consider a hidden variables model. This lambda means the element of reality that the experimenters cannot control and are responsible, at least probabilistically, of the outcomes of the observations. Okay, so now, besides the observed probability, one assumes that there is a hidden parameter lambda, which is responsible of what you observe in connection with the measurement choices. To fix ideas, imagine that they are measuring spin orientations. They are measuring spins, particles spins. Okay. So with these ideas, let me go fast. He rewrites the observed probabilities or correlations. So this quantity here is the probability of obtaining the results A and B if A chooses to measure spin in direction bolded A and Bob chooses to measure spin in direction bolded B. So by assuming hidden variables and by assuming a separability condition, so this equation here that I am remarking assumes that there is a hidden parameter lambda. And he says if there is locality, if Alice measurements actions cannot affect Bob's and vice versa, then we should have also this separability condition. So this is the locality assumption. And this is why this is called local realism. Realism because you use hidden parameters, and local because you have this separability condition. Okay, under those assumptions, in the end, there are more assumptions, but I will not go into the details. We can go if you have questions. So this is the observed probability, and this is the assumption that it can be rewritten under the hypothesis of local realism in this way. If you assume this, well, okay, Bell was able to derive inequalities. So the observed correlations between different types of Alice and Bob measurements obey certain inequalities, if local realism is correct. But as you know, quantum theory violates these inequalities. So it cannot happen that nature is described by local realism. So something is wrong. Either the locality assumption is wrong, either the realism assumption is wrong, or both. But they cannot be both compatible with what we observe because Bell inequalities are violated in nature. And also, it is very likely that you know more about this because in experiments, it is quite usual to use Clauser-Horn, Shimony-Holt inequality, which is like this. But what is important for me in this talk is that you understand, or you have at least an idea of these terms. These terms are correlations. For example, the first one means that Alice measures A and Bob measures B, and E. AB is the correlations observed between those observables. And then AB prime means that Bob, instead of choosing B, he chose B prime, and so on. There are combinations. So each party in this setting I will consider has two possible experiment to perform A and B, or I'm sorry, A and A prime, B and B prime, and there are 4 possible combinations. Combinations is called a measurement context. So there is a context AB, a context AB prime, A prime B, A prime B prime. There are 4. So what they do is to measure correlations on each context, and then they combine them in a single quantity. So if local realism is right, this combination should be lesser or equal than 2. And if it is not, local realism is violated. Okay. Okay. Well, of course, this inequality was experimentally tested. It took a lot of years to be sure about this, and of course, there's people making criticisms still, but there's not too many of them, I would say, nowadays. Because
I have a question. When people say when people refer to contextuality, they are referring to this concept or non-contextual scenarios.
Well,
like
it turns out that you can consider this as a special form of contextuality. Let us call it spatial contextuality, space-time contextuality, because you are assuming that somehow the quantum probabilities that will typically depend on the context, and there will be no global classical probability that will be able to model all possible correlations that you observe. You are assuming, you are forcing things as to a classical probability apart, because look at this, this is very important. Okay, the probability of Alice observing A being that she chose to measure bolt A and Bob chose to measure bolt B will not depend on what Bob is going to measure. So of course, here, this is a sort of locality condition, right? I mean, if the word is local, the results of my experiment will not depend on what you choose. This is, of course, related to the no signal condition, right? But if you had this sort of dependence on Bob's choice, that can be thought of as a form of contextuality. My point is that by doing this, you are forcing a classical probability in the description. And this is what is compatible, what is incompatible with quantum physics. Let me put it in another way. I could have prepared some slides about this. Okay. The point is this. If you consider different incompatible contexts, and you consider all these quantities among different contexts, so out of this you can compute the correlations, right? So now suppose that you have a classical, you want a classical probability model that reproduces all these correlations. Well, it turns out that if you put some hidden variables, it will not exist. And when you solve the system of equations, you will find negative probabilities. I can give you a paper about that because I work on that. So that means that, so to say in a rough way, that probabilities depend on the context in a very strong way. And if you want to force a global probability, look, there is another way in which you can see this. Lambda, the probability to obtain a certain value of the parameter lambda will not depend on Alice and Bob measurement choices. So in this way, you can see that lambda is global, and this is a very natural assumption because the source is considered to be independent of the Alice and Bob's choices, right? So this probability distribution that governs lambda will not depend on the measurement context. So in this way, you can see that these particular assumptions give place to non-contextual probabilities. So out of these non-contextual probabilities, you obtain a non-contextual inequality. But of course, this contextuality, this non-contextuality is related to space and time, because you are saying, okay, Alice is here, Bob is there, the source is here, the probabilities in the source do not depend on Alice and Bob's choices because of the assumption of locality and so on. This is all embedded in space-time discussions, but you can have a similar phenomenon without appealing to space-time in a single system. You can have contextuality in a spin 2 system, for example, or spin 1. Do you follow me, or am I?
Sí, totally. Sorry, you can totally go on. Thank you.
Yeah. But it is an important question, because I will do emphasis on this, on the fact that we will measure in different measurement contexts. So I think that the take-home message is that this contradiction with experiments, I mean, this tension between local realism and experiments appears because you are mixing here correlations that come from different measurement contexts. You are putting them all together in a single quantity. And this is what you should not do in quantum theory. This is what Bohr says. I will not reproduce Bohr's. Bohr replies to EPR argument, but it is very interesting. So you should not do counterfactuals. And by doing this, in some way you are doing it, because you are doing counterfactual reasoning, because you are assuming that, yeah, that this thing here will depend on a lambda that will not depend on the context. So in some point you are injecting a sort of classical probability model, and it doesn't work. Okay, it is very important. So this is nice for 2 particles, but for 3 particles or more, the game becomes more complicated, because you could have a situation like this. Suppose that you have a non-local state between this. I assume that you see the arrow. If not, you just let me know. But you might have non-local correlations between these 2, but perhaps the third one could be completely disentangled or completely uncorrelated. So this global state of 3 particles has non-local correlations, because there are non-local correlations between particles 1 and 2, but the third one is completely uncorrelated. So you need to distinguish between situations. It's important, and this happens with 3 or more particles. So here, when you have more than 3 particles or more, you need to appeal also to the concept of genuine multipartite non-locality. Okay. So for that scenarios, there are developments. For example, you have Svetlitch inequality, which I am copying here, the version. This is just one facet. So it is very similar to Clausen-Horn, Shimon-Holt. Okay, I don't want to enter into the details. You just need to know that in this scenario, you have 3 particles, Alice, Bob, and Charlie, and they can choose, each of them can choose between 2 observables. Alice can choose between A and A primed, Bob between B and B primed, Charlie between C and C primed. And then you have combinations, ABC, ABC prime. Each of these combinations represents a different measurement context. They are spin orientations. And these measurement contexts are incompatible. By looking for combinations in a smart way, you obtain this inequality in this infamous quantity, which combines incompatible measurement context. And so what is important is that if you prepare the system in a state that violates the above inequality, then it has genuine tripartite non-locality, okay? You are distinguishing between these two situations. For example, consider this state. It is the single state between the particles below, 1 and 2. They are prepared in a single state. But the third one is completely uncorrelated. So you want to discard a situation like this. Differently, the shared set state displays genuine multipartite non-locality. Okay, so you have this situation. So shared set violates this inequality, but this one will not violate. Okay, of course, you are in the same situation as in Bell's. The fact that the state will not violate the inequality, it doesn't mean that it is local. You don't know. It's a partial criterion. If it violates, you are sure that it displays genuine tripartite non-locality. But if it doesn't, you don't know. You are not sure because you don't know whether there exists a different inequality or different combination of observables that will give place to some form of non-locality. So it's a partial. It's not a criterion. It's a partial criterion.
I have a question, Fede.
Yeah.
Because this inequality, you can put in principle whatever you want, no, on the right-hand side of the.
Yeah, and
so on
whatever you want. Yeah. Let me add something that is crucial. Whatever you want means that you can add you can put a mixed state. It works also for noisy scenarios, and this is why you can use it in a quantum computer. Yeah. Please go on.
Okay. My question was linked to the definition of a genuine multipartite entanglement. If you define a genuine multipartite entanglement, as I understand from here, no, as a state that violates this Bell inequality, you in principle can construct different Bell inequalities, no?
Yeah, sure. Mm-hmm.
Okay.
Yeah, they are different. Yeah. It's a great question. Okay, let me tell you something. Let's go back to this. Just another slide. Okay, first, it is very important and crucial to say that entanglement is not the same as non-locality. I will speak about this. It should be written here. What is it? Okay, I don't know. Okay, but I'm telling it to you right now. Entanglement is not the same because you should look at this. I have this citation somewhere in the slides. You can show there's a famous Reinhard Werner's paper in which he shows that there exist states which are entangled, but still they do not violate Bell inequality. This is a hot topic in foundations of physics, which are the states that are entangled but do not violate any non-locality inequality. So, and there are states like that. So you can have entanglement without having non-locality. So entanglement is, you know, of course, the definition of entanglement, you know it, and perhaps you already know that the definition of non-locality, but you should be aware that they are not the same notion because you can have entanglement. And the point is that non-locality, with regard to the family, to a certain family of observables like this, like in this case, you consider a two qubits system and local spin measurements. So non-locality means that you cannot model correlations assuming this, okay? This is the definition. But entanglement means that the state will not obey a certain separability condition, which is, for example, it cannot be written as a convex combination of product states. That's the generalized definition of entanglement. But non-locality means this, that you can find, Bell non-locality, let us say, which is local realism. It's a very specific form of non-locality. So you cannot rewrite the correlations in such a way that they can be described with the local hidden variable models. This is non-locality. So they are not the same notion. And so very important question. Your question is very important because now you say, okay, how do you define genuine multipartite non-locality? Okay, it must happen. So what Svetlichny inequality discards is hybrid local realism models. Because it might happen, for example, what is the difference between this situation and this situation? This situation, I am just explaining it. You're not obliged to understand this because I didn't tell you. This situation means that if you consider any bipartition of the system like this and these two and all the possibilities, there is no local realism between any bipartition. But in this case, there is, because you don't have local realism between particles 1 and 2. But if you consider the subsystems particle 3 and particles 1 and 2 together, there will be local realism between 1, 2, and 3. Do you follow me?
Oui.
Yes. So I'm not giving all the technical details, but the idea is that similarly to the 2 qubits case, where you define local realism in this way, because you only have 2 parties. If you have 2 qubits, there is only one way to make a bipartition of the system. So if the correlations obey something like this, you say that the system is governed by local realism. But when you have 3 particles, there are different partitions. For example, this partition, the particles on bottom and the particle on top. This is one possible bipartition. In this case, for a state like this, you can have local realism between particles 1 and 2 and particle 3. Okay? But in this case, you don't have hybrid local realism. So in this state, the state on top, you have some non-locality. Yes, of course, this state is non-local, and it will violate certain non-locality inequalities that are not as strong as Svetlichny's. So this is what is crucial for us. We are using not just non-locality, we are using genuine multipartite non-locality. This is perhaps what is special about our work. Because, of course, if you Google about the topic, if you Google violation of Bell type inequalities in quantum computers, you will find a lot of works, and you will find that it is possible to go quite far in the number of qubits. And again, you might have heard about recent IBM's works where they claim that they find 120. Shagan Beta is saying that he can violate. Not violate, but he can prepare a genuine entangled state with 120 qubits or something like that. Okay, but it is different. This is different because one thing is entanglement, like genuine multipartite entanglement, is a concept. A different concept is non-locality, simple non-locality, and still a different concept is genuine multipartite non-locality. Is this clear?
So does it also mean that if you run let's go back to this one, you run the genuine 3-party non-locality test, using in a 100 qubit computer, taking triplets of 3 different qubits many times, you didn't test the 100 qubits. It's you did many tests of 3 multipartite non-locality, but not for 100 qubits.
Mm-hmm.
It's not the same testing pairs, testing triplets, or 4.
Yeah. These are all different tests, because I was going to say it.
And this means, so just so I understand it, is the more elements you can have in the system that you can ensure that they are genuine, non-locality, whatever, the better your computer.
Exactly.
That's the idea.
That's our proposal. That's our proposal, and then I will show you numericals and some experiments on actual.
And I guess that adding more, going from a pair of qubits to 3 adds more complexity, and getting to 4 or 5, it's even more and more complex, right?
Absolutely. Yeah. Okay. Exactly. That is the case. But what I will stress in the end is that even experiments for a small number of qubits are very informative about how at least quantum computers nowadays work. I will show you. But yeah, so this I am focusing here on the 3 particles case, but this can be extended to n particles. Okay, you can have there's a formula for Svetlichny inequality for n qubits, like with arbitrary n. Of course, to test a bigger number of qubits becomes harder and harder. It is exponential because you need a lot of context. Okay, so it's very difficult to do a big test about this. But still, I will show you numericals, and you will see what happens, and some experiments, and you will try to understand why we propose this as a methodology for assessing the performance, because we will mix this with quantum random circuits, and you will see why this will give you a very good idea of the state of the quantum computer overall. And of course, if you are informed about the calibration of a quantum computer, it's very usual to communicate how qubits are behaving individually, like coherence times and so on. But also, you are being communicated 1 qubit and 2 qubit gates. So now, if you make tests on triplets and you have information about triplets, this is stronger. You are obtaining more information, and if instead of considering triplets, you consider 4 particles, it is more and more. So the further you can go in the number of qubits, the better. But as you can see, I mean, what we find is that still already for 4 qubits, it's very challenging. 4, 5, 6 qubits, it becomes challenging with quantum computers nowadays. So this is why this kind of tests can be very useful now and for many years, because okay, let me go on.
It becomes complex to run the test, or that the computer passes it?
No, we find very different behaviors. That's the point. Between different triplets of qubits and between different computers, they are very different. Yeah, that's the point. Yeah, so in general, and you know this, in general, ion trap architectures perform much better than superconducting qubits architectures. You know this, because also, if you want to test this inequality, all types, this is affected by different types of noise. Readout noise is important too, and readout noise is much stronger in superconducting qubits than ion trap. Okay, this was my critical observation. Non-locality is not the same as entanglement, so this is a stronger test than just testing entanglement. And also, well, this is the paper that I was talking about. Perhaps you can have a check on this. But also our paper, we give some more information about this. This is quite important. So why is this so hard? Okay, this is a copy of Garnet, an IQM device. It is called Garnet. This is the topology. And suppose that you want to test non-locality between qubits 1, 2, and 4. These are connected, okay? I mean, connected by the possibility of applying local entangling gates, okay? Of course, you could test 1, 18, and 17, but well, this test will give a very bad result because these qubits are not directly connected. So you will see a total difference between the results. I mean, for us, it is pointless at this stage of development of quantum computers. But suppose that you choose 4, 1, and 2, okay? So this will be Alice, Bob, and Charlie. And each of them will have 2 local spin measurements. In a quantum computer, you can model a local spin measurement by applying a rotation. So before, because usually quantum computers make measurements in the computational basis. So what we do in order to mimic different measurement contexts is to apply local rotations. So in this way, you can define any spin measurement you want. And there is something very important here, because if I show you a violation of this inequalities example in a quantum computer, you will say, well, how can you be sure that this is non-locality? Am I allowed to claim that I found non-locality in IBM's or whatever IonQ quantum computer if I show you some of these tests? Well, it is really tricky because qubits are so close. So how do you know that the statistics you are obtaining I mean, that there's no signaling condition is being fulfilled? The qubits might be very well connected because you are not testing the measurements that you perform. You are not granting that they occur in space, that they obey the space-like separation condition of relativity. So I think that what is safe to say and what is reasonable to say is that we are simulating non-locality in a quantum computer. Not testing non-locality is very different, because qubits are so close. You are not under the conditions of a loophole-free test of non-locality. So a guy who is against quantum non-locality will come and say, okay, this is full of loopholes. You are not granting the conditions that you impose on these experiments are not enough to grant non-locality. Okay, it is true. I agree, absolutely. And this is why I propose to call this simulation of non-locality in quantum computers. And this is a crucial debate, because I will talk about this later if I have time. If you believe that quantum advantage or supremacy is due to non-locality, well, then you have a problem, because you should show that quantum computers are non-local. How can you do that? It's a very difficult experiment, I believe. And okay, but then if you are of the family of people who believes that the reason for quantum advantage is contextuality, well, then you are not forced to do that test. But what is fascinating for me is that this type of simulation is related to a foundations of physics debate that is also related to technology. So you're mixing foundations of physics here with technology development, because at some point you need to know what is the reason for quantum advantage. What are the resources that are responsible for a difference between quantum and classical computers. That's a hot topic in quantum computing and foundations of physics. I will talk about that in a minute. So I hope you understand that what we do here is to choose the qubits first, and then we choose the spin orientations associated to the different measurement contexts. And these spin orientations are simulated in the quantum computer with local rotation. So a quantum state, suppose that you have 3 qubits, a quantum state will be just a combination of quantum gates that will end up preparing the 3 qubits in a certain mixed state row, because we are considering noise here. The computer could be noisy. If there is no noise, the state should be pure, but if you do experiment, it will be mixed. And for each state preparation, this is how you model the preparation of a quantum state. This is the source. This is the source of Alice and Bob sending them the particles, okay? Alice, Bob, and Charlie. And then Alice, Bob, and Charlie must model or mimic the local measurements with an extra layer of circuits. And each combination between states and local state preparation and local measurements will give you a correlation term. This E means one of the correlation terms in an inequality. And there will be, for example, for 3 qubits, 8 of them, E1, E2, and so on. And then you go on, perform you need to specify a number of shots for each one of them, usually the same number. And this is how you obtain empirically the correlations. Then you will combine them in a classical computer and check whether the inequality is violated or not. And this is how you simulate, or at least how we simulate, non-locality in a quantum computer. I think all of this is crucial. And then why is this so hard? Well, because you need several measurement contexts. There are tests that measure a quantum state or perform measurements in a single context. Here we are combining different measurement contexts. And typically this will consume non-Clifford resources. So in some sense, this test implies that you need some magic to obtain a good simulation. So this is why the test is so hard. You are using really different measurement contexts. So okay. So now I will go into the details. Oh, I don't know. Okay, Matthias, you let me know about time.
Yes, in principle, I think it would be very, very nice to sum up in like 10
minutes. Okay.
Yeah, I think it will be reasonable.
Okay. So I will go fast with the results. So this is a joint work with the Cagliari group. And if you want more details, you can go to this paper. Okay. So as a summary, simulation of big Hamiltonians is one of the promising things about quantum computers, but then we ask about genuine multipartite non-locality. So then we ask, why supremacy or advantage? We study how genuine multipartite non-locality is distributed in combination with quantum random circuits. This is relevant for technology and quantum foundations. And so this is related to questions like why quantum dynamics seems to be essentially different from classical dynamics. What is the essence of quantumness? Is quantum non-locality essential for quantum advantage? Okay, I will try to give some discussion about this. Let me go fast. Okay, quantum state space grows as 2 to the power of n, and this is difficult to simulate, but quantumness matters. It is not just the dimension, because you have results such as Gottesman-Neal theorem, in which you can efficiently simulate the sampling over a quantum computer that uses only Clifford resources. You can do it with a probabilistic Turing machine. And it is also important for certification, because In the NISQ era, you can ask up to which point a given quantum device is able to generate the whole quantum state space. So combining quantum random circuits with the non-locality test, we get a very nice snapshot. So what is quantum random circuit? Suppose that you want to explore the quantum state space, and you cannot do a calculation for each possible state because there are infinitely many of them. And so assume that you have some form of rain that rains uniformly. When rain comes, it comes for everyone in a uniform way. In average, I will receive the same rain as Matthias if we are in the open field because rain falls uniformly. So quantum random circuits, what they do is to produce random unitaries that will allow you to explore the quantum state space in a uniform way. So you will obtain samples of each region of the quantum state space with uniform probability. So it is a fair sampling, so to say, of the quantum state space. And by doing this, you can compute volumes. For example, if you compute the percentage of states that have some property and then compare it in size, in number, with the percentage of states that do not possess the property, then you can compute or measure relative volumes. So what we do is to produce quantum random circuits. And if you, for each one of the states produced, you compute the non-locality, you compute whether they violate or not, or the maximal violation value of the Svetlichin inequality, you obtain a histogram like this, okay? And you can do it for 2 qubits, 3 qubits, 4 qubits, 5 qubits. What we obtain is very interesting because for this particular phase, the violation percentage tends to 0. This is interesting in itself. And if you compare the results with Mermin inequality, which is a similar inequality, but testing only non-locality, you get that a lot of non-local states. So most of these states are non-local with regard to Mermin, but not with regard to this particular phase that we are using of the Svetlichin. So this allows us to formulate the question, what happens with the relative volume of genuine multipartite non-local states? This is an unknown, this has no known solution up to now. So we are formulating the problem. What is the relative volume of the set of genuine multipartite non-local states? One possible conjecture could be that it tends to 0. And the fact that the Svetlichin inequality is not violated will not preclude, in principle, other non-locality inequalities to be tested, because there could be other phases. It's a very hard problem. So the answer is not obvious, but there is a very interesting problem for geometry of quantum mechanics here, because so in this plot, we show the histogram. In pink, at the bottom, you have no noise. So this is the ideal histogram. Should your computer work perfect, you should obtain this histogram independently of the universal set of cases that you use. So the shape of the histogram will not depend on the architecture. This is important. It's crucial because if you do it with the IBM quantum computer or IonQ quantum computer, if they work perfectly, you should obtain the pink histogram. But if you add noise, of course, the histogram goes to the left because non-locality will be destroyed as noise grows. So by comparing empirical histogram with theoretical histogram, we have a very good idea of how this triplet of qubits is working, because in a global way, because quantum random circuits explore any possible circuit. You are getting, so to say, close to any possible quantum circuit that you can prepare on your quantum computer. So ideally, if you can do these histograms and compare experiment with theory, you have a very fair test of a quantum computer, which is, so to say, independent of the architecture. Because should your computer were perfect, you should obtain the same result independently of the architecture. And the fact that you are considering random circuits means that the problem will not be in the optimization you are using. You can use transpilation, of course, but you can just use native gates, and in that way you forget about the problem of writing the circuits in an efficient way. Because if you use a shared set state, and then you need to worry about writing it in terms of native gates, then you could blame the optimization. But if you just choose random circuits based on native gates, you don't have that problem. Okay, and also this is the same histograms, the same idea, but instead of using a universal set of gates, we restrict to the Clifford sets. So as you can see, the main difference between Clifford and a universal set is not the fact that you can obtain maximal non-locality, because you can do that with both, but the fact that in the Clifford set, the values of non-locality are distributed in discrete sets. This is very important because the Clifford set is classically simulable in an efficient way, but it is assumed in quantum computing that Clifford plus T has magic, and so it cannot be efficiently simulated, or at least there will be circuits that cannot be efficiently simulated, or algorithms. But the main difference is not how much non-locality you have, but the main difference is how non-locality is distributed. So, question: is the discreteness of this distribution responsible for the fact that this set is classically simulable? Well, we think that perhaps there is something like this going on. This is important for us. Okay. Also, you can make a comparison with entanglement, but I will just skip that. And I will end the talk, just speaking about some implementation on quantum processors. As I told you, what we did is using Amazon Bracket. We did some, so I will communicate here some experiments that we did in IQM and IonQ. We use Amazon Bracket for us. Our goal is to develop theoretical tools and useful software that is plug and play and easy for end users. We will publish the codes very soon. Part of the codes are already published, so you can use them. But we are preparing an updated version that you will be able to use. I explained you already how we do the experiment, so we'll not go into the details. And this is a very nice example because we didn't reproduce the full histogram, but what we did is to choose from each. We divided the histogram in subintervals and extracted some particular circuits that are representative of each violation value and repeated them 10 times. So these points here mean that we repeated a non-locality test 10 times. So you have a dispersion of the same thing, which is natural due to finite statistics. But what is important, this is IQM, is that in black cross here, you have the ideal value that you should have obtained should the computer work perfect, but it is not, of course. And by doing a histogram like this, you have a very concrete idea of how this triplet of qubits is working, because you have a very huge gap between ideal and the experimental test. And you can do this for different triplets and get it, or you can, instead of triplets, you can consider 4 qubits, 5 qubits, 6 qubits. And this is, for example, a comparison between IonQ and IQM. The green dots are IonQ and the red dots are IQM. This was surprising for us because they are very close, but not so, because when you have 3 qubits, things look okay in the sense of similarity between IonQ and IQM. But when you go to 4, 5, 6, whatever qubits you want to, so it was not possible to simulate violation of expectation inequality with IQM. This is important. And when we did more experiments, we have a lot of experiments now, but are not published yet. We are working on a paper. So let me go to this. Now we are working in close connection with the team of the Leibniz Rechenzentrum to use and improve this non-locality benchmark tool to test quantum processor, the names of the people involved. And we are now conducting experiments on an IQM machine, which is in Munich, and an IQT machine, which is also in Munich. And we find similar results. Ion trap performs much better than superconducting qubits. And when you scale the number of qubits, the results tend to go down. And also we find that violating Svetlichin inequality is naturally harder than finding a violation of Mermin inequality, which is testing simple non-locality. Okay, some references. The content of this talk is contained in this archive preprint. The paper is not exactly the same because we've been doing modifications, but very soon we'll publish the updated version. And if you want to read more about contextuality, I recommend you to go to this paper, which will be published, I think, soon. But you can go to the archive place. And also, if you are interested in the deep philosophical foundations of this methodology, if you want to know, I wrote this conceptual paper that perhaps can be of interest for you.